is CO2, water, and some additional SO2 and NO. And this is the conventional system which we showed for natural gas. There are no changes. We have one advantage in that there is a lot of low-grade heat available in a gasification process, particularly if you're using a quench from water, or in this case we showed a quench from liquid CO2. But water quench is the more usual, and so we have a lot of... Oh, damn. Sorry about that. The low-grade heat here is what we need for putting the heat into this power cycle. So this again gives you a very big boost in the efficiency of the gasifier. Next slide. Now, what happens to these impurities? Well, actually this conundrum was solved by the old alchemists in the 13th and 14th century. They tried to make sulfuric acid, and they couldn't make sulfuric acid by burning sulfur-containing minerals in air. But they found that if they produced some nitrogen oxide, some nitrogen dioxide, by burning saltpeter, they could use this reaction. Nitrogen dioxide reacts with SO2 instantly almost to form SO3. So if you have liquid water present, the SO3 will immediately form sulfuric acid. And these are very fast reactions. Now, in our system, we have nitrogen oxide, but we have excess oxygen. And we have a high pressure. And this reaction is a free radical reaction, which is second or third order. And therefore, increasing the pressure increases the speed of this reaction. So the fact that we're operating our water scrubbing system at 30 bars pressure means that this reaction takes place quite fast. It's called a slow reaction because it takes a second or two to happen, whereas these are virtually instant. And the nitrogen oxide is slowly converted to nitric acid. So if you design your water contactor with a residence time of a few seconds, you can produce a system without any further purification required, in which the SOx level is sent down to about 2 parts per million, and the NOx level is just a few parts per million. The sulfur dioxide level is virtually indetectable. This system has been verified in pilot plant conditions in both the US, UK, in Australia, where there's a lot of interest in this process, and it works perfectly. In fact, the system will work down to a pressure of about 10 bars. So our pressure of 30 bars with a residence time in the direct contact cooler of just a few seconds is an excellent solution. Next slide. I wanted to show you that for coal, the best estimates we did, I must admit, we did these a few years ago, about 2018. But basically, this is the cost of a full CCS removal on a bituminous coal under US conditions. And this is the current cost of a supercritical conventional pulverized coal-fired power station. So we can reduce the cost for this system compared to an ordinary coal-fired power station with all its CO2 being emitted to atmosphere. Of course, if you put CO2 removal on this power station, it's roughly double the cost. And if you use IGCC on coal with carbon capture, it gives you about the same cost, which again is double the cost of this system. So this system is not just an option for future coal systems. It's really the only way that you'll be able to tackle future coal-fired systems. And it will give you a very good saving over what people are doing at the moment. And that's really all you're looking for. We can capture the CO2 and we can reduce the cost at the same time. So this is a really important way in which zero carbon emission can be achieved in countries which rely on coal as their fuel source. Next slide. So for transportation, as I showed you, the BP figures showed about 8 gigatons of CO2 emission in 2018. And that was about 24% of total man-made CO2 emissions. And current CO2 targets use battery-powered vehicles and phasing out of combustion engines. In the UK, we're not going to have any more cars sold with diesel or petrol engines by 2030. So, and hybrids will be phased out in 36. Other countries have different regulations. This requires a massive increase in CO2-free power for battery charging. There's no point in putting batteries in cars and charging them from power stations which are emitting CO2 into the atmosphere. The only effect of that is to clean up our cities, which is very important, but the objective of CO2 removal from the atmosphere is paramount. The other thing we have to recognize is that in many countries, there's more emphasis on providing power to communities which aren't at the moment able to use power generated centrally. They're relying on their own individual distributed power systems. So this business of phasing out hydrocarbons for transportation will not be uniform in the world, and there'll be a good deal of hydrocarbons used, as I showed. So the alum cycle power plants offer the lowest cost alternative for this extra power. Renewables alone will not be sufficient. Renewables are challenged very much. The amount of new renewable capacity we need, I showed, would be very, very high. The second alternative to battery power would be based on hydrogen fuel cells. And this is where we start to talk about the hydrogen economy. These things are based on proton exchange membranes, which operate at temperatures of around 70 or 80 degrees centigrade. And these can be used to power lorries and trains and light aircraft, which have power demands where batteries would be too heavy. Think of the amount of emission from ships, which all run on various types of hydrocarbon fuel. So trying to drive a ship with the batteries would be quite impossible. So particularly with heavy lorries, with large range requirements, if you want to drive a heavy lorry with a fuel load for 1,000 kilometers, you'd need some very, very heavy batteries. It'd be totally impossible. And the other point is that hydrogen fuel cell vehicles mean that you don't have to buy this additional electricity generating capacity. The hydrogen can be produced in separate hydrogen plants using mainly natural gas as the fuel. And of course, there is the dialogue at the moment between green and blue hydrogen. And I think as far as hydrocarbon fuels and hydrogen propulsion systems, I think you're going to find that the two systems will probably coexist in the future, and that hydrogen use in these applications where large power demands exist will become more and more important. Next slide. So green hydrogen produced by electrolysis using excess power generated by renewables and nuclear during periods of low power demand from the grid. That's the concept. But I think people have to realize that it requires a very heavy investment, about 1,000 kilowatts per kilogram, $1,000 per kilowatt of power. And that's a projected cost. Current costs are higher than that. And the power is about 5 kilowatt hours per normal meter cube of hydrogen. It requires nearly a lot of power for producing the DC current required for the electrolysis. So the conventional idea that you can electrolyze at 4.2 kilowatts per kilogram, that's when you've got the DC power already produced. If you're using power off the grid, it's going to cost you that much. Now, if you make blue hydrogen, I've been working on a new concept for making blue hydrogen. We've been working on it, or I've been working on it for the last couple of years. And I've now developed this to the point where we're filing patents. We'll be disclosing this in the next few months. But basically, this system has 100% CO2 capture from natural gas or light hydrocarbon fuel. It produces the CO2 at 150 bars pressure, and the hydrogen is available at 25 bars to 80 bars pressure. And the thermal efficiency, which is the heating value of the hydrogen over the heating value of the total natural gas required, is about 75%. And it will have a relatively low capital cost. And I think this is going to be one of the choices for new hydrogen capacity worldwide. The plant size, it's a very compact plant which can be built in modular form. The plant sizes required for these new applications will be very large, in the range of 100,000 to 500,000 normal meter cube per hour. The important point is we can use natural gas pipelines to convey hydrogen to users, but we can't convey quite as much thermal energy when we're in the form of hydrogen compared to natural gas. But it's not bad. I think it's about 70%. The other thing that we need to understand is that we have to look at the hydrogen distribution system. Hydrogen is a very expensive material to distribute. We must try and get this hydrogen conveying by pipeline established, particularly in urban areas. But there are going to be a lot of areas which are not amenable to supply by pipeline. In this case, in many countries where LNG is imported, there is an opportunity to integrate hydrogen liquefaction with LNG revaporization, where there is a huge amount of refrigeration available. And this effectively reduces the power demand for liquefying hydrogen to about 2-3 kilowatt hours per kilogram from a conventional standalone plant, which takes about 9.5 kilowatt hours per kilogram. Next slide. These filling stations for ultra high pressure hydrogen have been in existence since about 2000 or 2002. The first two stations which my old company, Air Products, built were for BP in Singapore, this one here, and for Shell in Washington, DC. And these stations have been in operation for quite a few years. Next slide. And this is the Washington DC fueling system. There's an underground liquid hydrogen tank, and above ground is a valve and instrumentation package. Liquid hydrogen is a complicated material, and it needs a bit of care and attention. So this is the sort of structure that you need for the valves and the safety devices and the instrumentation. And this then goes to a high pressure pump, which pumps the liquid hydrogen to 700 bars pressure. So the fluid going into the into the cars or into the dispenser is hydrogen at 700 bars, and the dispenser has a special devices that make that a safe material for filling into the car's tank. So that's it. I've tried to explain to you the way in which fossil fuels can be used to produce clean energy, both in the form of carbon-free power or natural gas, using natural gas or coal as fuel, and also as fuel with 100% carbon capture, using again coal or natural gas to produce pure hydrogen for use in the hydrogen economy. So thanks very much for your attention.
Okay, thank you very much, Professor Alum. And please, dear colleagues, questions?
Yeah, Professor Alum, hello once again. Thank you very much for your lecture. It was quite amazing and interesting for me. And I have a question about oxygen. In your cycle, you use oxygen for combustion of methane. And what's the source? How would you like to produce this oxygen? And how does it influence to the resulting efficiency of the power plant working on Alum cycle?
The power efficiency that I showed you, 57% of the commercial plant, includes all the power for a cryogenic air separation plant. So the plants can produce oxygen at pressures of up to 300 bars. But the way I've shown the cycle, the oxygen will be produced at about 120 bars, mixed with CO2 and compressed as a gas at 300 bars. Now you ask what the future might bring. Well, there is another method of making from the air. You can separate oxygen from the air using process. The free energy of oxygen at equilibrium in a combustion process is vanishingly small, whereas at atmospheric pressure it can be thought about as being equivalent to the partial pressure of oxygen, which is a 0.2 of a bar. So there is a huge driving force for diffusion across an ion transport membrane, because it's actually a short-circuited electrochemical cell with the metal ions transmitting electrons and the oxygen ions being ionized and passing through the material. And these things have been tested at a large scale, and they do work. They work for combustion, and they also work for separation of pure oxygen. So that in the future, these plants are going to incorporate their own oxygen plants. And this is particularly true for smaller versions, where you can keep the temperature for the turbine down to 900 to 1000 C. You still get a pretty good efficiency. And so these systems are under development, and they'll be produced in the next 5 or 10 years.
Yeah, thank you very much.
Thank you very much, dear colleagues. Maybe more question? Yes, please.
Thank you, Professor. My name is Anthony. I just have two simple questions. First is about the new type of turbine. I wanted to ask the challenges you are facing in terms of it being taken on by people who manufacture turbines, because it is a new concept and it requires a lot of money, so there must be resistance in terms. Yes, that's the first one. Then the second one is about the theory of hydrogen fuels being taken up in the automotive industry. the way you've talked about the challenges of hydrogen in distribution, manufacturing, storage, and handling, my question is it really applicable? Because right now it's facing a big competition of using electric batteries, lithium batteries in the transport system. So, if it is to be taken on, to me personally, I have bias on the electric batteries. So, I believe hydrogen can be the solution. But why is it taking long to be taken on, irrespective of the challenges they have in terms of distribution and that? Is it a myth or it is really applicable, and how safe is it to be used? Thank you.
Well, it's one of the biggest challenges. The turbine manufacturers will not do this unless they believe there's a huge market. But over the last 2 or 3 years, the perception that this market is really there and is going to grow vastly in the future has been really increased by the fact that we are now much more aware of the need for cleaning up the atmosphere. This has become the most pressing problem, really, for mankind, after COVID, perhaps, that we face. And so as this perception becomes stronger and stronger, the manufacturers will look around and decide whether the system that we use, that I invented, the CO2 power cycle, or perhaps other systems which are better than mine, which would still use maybe CO2 as the working fluid or maybe something else. But whatever it is, they will be faced with the problem of how they enter this market and satisfy demand. And we're already in the point in the US where we have 2 commercial plants which are under design and are going to be constructed. And these were announced just a few weeks ago. And one is in Colorado, the state of Colorado, and one is in Illinois. And both of those will have turbines. And at the moment, gas turbine companies worldwide are considering quoting for those machines because those are real requirements and we're going to be buying them within the next 2 or 3 years. Now, as far as the second point goes, it depends, as a lot of things do, on the perception and requirements of customers. Here we're in the position of the world population having a choice as to which cars they want to buy. And we'll have to see over the next 10 or 15 years whether they're happy to buy battery-powered cars or whether they're happy to buy fuel cell cars. And both types are available in the market right now. Now, if you live in California or in the western part of the United States and your general car journeys are several times a year, you're taking journeys of hundreds of miles, maybe 500 miles, maybe 1,000 miles. You don't want to stop every 200 miles to charge your battery, particularly as you've got to find a charging point, and that might not be available. People in a city, on the other hand, may never, in the whole of their life of their car, or maybe they've got 2 cars, and they'll have one for city and one for the general driving in the country for long distances. So I think both systems will coexist. And it's quite clear that if you have a lorry with a 300 or 400 kilowatt engine, and you want to have 1,000 kilometers of range, which a normal lorry has with its size of diesel tank, then you're going to require several tons of batteries. And it's quite infeasible for you to think about using batteries in heavy lorries. And when you come to ships, it's even worse. And certainly for things like taxis and buses in cities, fuel cells are the natural choice. So I think that's the answer to the question. The people will decide.
Yeah, thank you very much. Do you have any questions? And maybe if it's possible, I also have a question for Professor Alam. What do you think? We have a strategic global goal, and we need to solve problem of decarbonization. And do you believe that in 30 years it's possible to solve this problem of decarbonization in energy sector?
Well, I think really we can do it with natural gas, but the real problem is, can we do it with coal? And all I can say is that if you build a power station now, and it's a supercritical pulverized coal power station, and I'd like you to think of the power station which is being built or proposed by Shenhua in, I think it's in Western China somewhere, but it's 8,000 megawatts, and it's on coal. Now that station will have about a 40-year life, but at the end of 40 years, which is in 2060, it will have to be replaced. And at that point, you can put in the coal gasification CO2 power cycle that I showed you. So the answer really, as far as I can see, is that this type of CO2 power system coupled to a gasifier has to be introduced immediately. It's very urgent, at a full size, to demonstrate that it can be used to replace an existing power station coming offline. And if that's done, for example, in China or in Russia, then I would say that in 5 years, you could be demonstrating the first plant. And from that point onwards, you can build up the infrastructure for replacing each plant as it comes offline. So I can't see that you're going to do it in less than a 40-year timescale and allow another 5 years up front to get the first demonstration system sorted out. So you've got to be looking between now and probably 2065 before you've really completely replaced the whole kit. That's the only way I can see of doing it.
Mm-hmm. Okay, thank you very much. Okay, dear colleagues, I can say thank you very much to our Professor Alam for your brilliant, interesting lecture. And I'm sure that all this mission of new energy and new generation, and it's very useful to understand all ideas that we have in modern energy sector, because I think we live in a new reality, and we form our close future. And it seems to me, I'm very glad that it's an international conversation, because in my opinion, only one country, it's impossible to solve this problem. It's global goals, global ideas, and
it's a global problem.
Global problem, yeah. We can manage it only together, and that's why I thank very much to all our participants of this meeting, and I'm really glad to see different people from different regions, and I hope it's our mission to organize this community and to maybe to bring these ideas to society, to everybody, to understand that it's very important. Thank you very much. It's a great thanks to everybody. Health and care and be care. And this I close our meeting, and best wishes to everybody. Thank you very much. Thank you very much.
Thank you.
Thank you very much.